Chapter 8 Helicopter Performance Introduction is imperative for the student to realize safety correlates directly to a comprehensive understanding of performance planning. Performance planning incorporates engine power available and rotor system efficiency to establish helicopter performance values. The student must be able to recognize the impact of density, altitude, helicopter weight, and other environmental factors in order to maximize each helicopter's unique capabilities, while understanding its limitations. Failure to conduct performance planning properly may lead to disastrous consequences. Factors affecting performance. Instructors should ensure the student has a firm grasp on the four major factors affecting helicopter performance: density, altitude, weight, loads, and wind. Emphasis must be placed on the importance of proper and thorough performance planning prior to each flight. Density, altitude. The instructor should convey to the student the need for a comprehensive knowledge of density, altitude. The student must understand what combinations of high elevations, low atmospheric pressure, high temperatures, and high humidity directly impact density, altitude and its effect on helicopter performance. Explain that density altitude is pressure altitude corrected for non-standard temperature. High density altitude refers to thin air while low density altitude refers to dense air. Figure 8.1, air density is affected by changes in altitude, temperature, and humidity. Conditions that result in a high density altitude are high elevations, low atmospheric pressures, high temperatures, high humidity, or some combination of these factors. Lower elevations, high atmospheric pressure, low temperatures, and low humidity are more indicative of low density altitude. Using the building block concept, explain the factors that may increase or decrease density altitude. The predominant factors are atmospheric pressure, altitude, temperature, and moisture. Use examples of each factor's impact on the performance planning used for the aircraft to be flown. Stressing the impact that each factor has on density altitude leads to a greater awareness of the student to these ambient conditions. The lift equation is an effective tool that can be used to show the effect of an increase or decrease of density altitude on aircraft performance. Lift equals coefficient of lift x density x velocity 2x lifting surface area 2. Once the student has a clear understanding of how density altitude affects helicopter performance, you can advance to actual flight demonstrations and hands-on practice. The instructor can set artificial limitations on the amount of available torque or temperature to simulate operations in environments that cause actual reductions in power margins. While this provides a demonstration to the student, it is not a substitute for actual conditions. The instructor could ask the student to determine performance for a maneuver, such as OG hover, for a low or field elevation, and then for one at a much higher altitude normally found in the area of flight. Then, the instructor could discuss the difference with the student and ask the student to describe the practical response differences of the helicopter in the two situations. The instructor may be able to simulate higher elevation power of the helicopter performance by artificially limiting the power the student can use, for example, limit the manifold pressure or torque to be used. However, the instructor cannot limit the lift and efficiency of the rotor system. The instructor must ensure the student understands the lack of fidelity of the simulation and the hazards awaiting the pilot at high density altitudes, such as lower VNE, less anti-torque available, less lift from the rotor system, slower engine response, and higher collective pitch settings for cruise and hovering. If the student makes errors during the simulated high-altitude practice, the increased power is still there, whereas the power is simply not there at actual higher altitudes. At higher altitudes, helicopters do not have the margins of performance necessary to correct errors in planning or judgment. Due to the retreating blade stall characteristic of helicopters, increasing altitudes yield no performance improvements over 5,000 feet to 6,000 feet depending on the design and power plants. Therefore, when operating in higher terrain, any altitude gains above takeoff elevation usually results in decreasing performance. By the very nature of a helicopter, a pilot must be versed in the performance limitations imposed by the change in the environment. The pilot must understand the limitations of increased altitudes and plan accordingly. Therefore, the instructor must include that planning in the syllabus. Refer to Chapter 10 of the Pilot's Handbook of Aeronautical Knowledge, FAA-H-8083-4, for a detailed explanation of density altitude as it relates to aircraft performance, and Chapter 3 for more information on the structure of our atmosphere. Weight. The student should possess a basic understanding of the aerodynamics of weight opposing lift. As the weight of the helicopter increases, the power required to produce lift also must increase. The instructor should use the helicopter's performance charts and the relevant pilot's operating handbook, POH, to demonstrate minimum and maximum weight configurations, and how that correlates to required power with a given set of environmental conditions. A beneficial technique is to show various power/torque requirements at graduated weight and altitude increments, culminating with high gross weight/high altitude condition. This demonstrates the additional power required as weight and/or density altitude increase. Validation of this exercise can be accomplished using similar data and performance charts while flying at various weights and altitudes and noting the corresponding torque values, or using fuel weight at various stages of the flight. As fuel, i.e., weight, is burned off, power requirements decrease. This gives the student a practical application of his planning. Loads. The strength of the helicopter is measured by the total load the rotor blades are capable of carrying without causing permanent damage. The load imposed upon the rotor blades depends largely on the type of flight. The blades must support not only the weight of the helicopter and its contents, gross weight, but also the additional loads imposed during maneuvers. In straight and level flight, the rotor blades support a weight equal to the helicopter and its contents. So long as the helicopter is moving at a constant altitude and airspeed in a straight line, the load on the blades remains constant. When the helicopter assumes a curved flight path, all types of turns, except hovering turns utilizing pedals only, flares, and pullouts from dives, the actual load on the blades is much greater because of the centrifugal force produced by the curved flight. This additional load results in the development of much greater stresses on the rotor blades. Load factor. The load factor is the actual load on the rotor blades at any time, divided by the normal load or gross weight of the helicopter and its contents. Any time a helicopter flies in a curved flight path, the load supported by the rotor blades is greater than the total weight of the helicopter. The tighter the curved flight path, that is, the steeper the bank, or the more rapid the flare or pullout from a dive, the greater the load supported by the rotor, therefore, the greater the load factor. The load factor and, hence, apparent gross weight increase is relatively small in banks up to 30 degrees. Even so, under the right set of adverse circumstances, such as high density altitude, gusty air, high gross weight, and poor pilot technique, sufficient power may not be available to maintain altitude and airspeed. Above 30 degrees of bank, the apparent increase in gross weight soars. At 30 degrees of bank, the apparent increase is only 16%, but at 60 degrees, it is 100%. If the weight of the helicopter is 1,600 pounds, the weight supported by the rotor in a 30 degrees bank at a constant altitude would be 1,856 pounds, 1,600 plus 256. In a 60 degrees bank, it would be 3,200 pounds, and in an 80 degrees bank, it would be almost 6 times as much or 8,000 pounds. One additional cause of large load factors is rough or turbulent air. The severe vertical gust produced by turbulence can cause a sudden increase in angle of attack, resulting in increased rotor blade loads that are resisted by the inertia of the helicopter. To be certificated by the Federal Aviation Administration, FAA, each helicopter must have a maximum permissible limit load factor that should not be exceeded. As a pilot, you should have the basic information necessary to fly a helicopter safely within its structural limitations. Be familiar with the situations in which the load factor may approach maximum and avoid them. If you meet such situations inadvertently, you must know the proper technique. Wind. Much like density altitude, awareness of the wind's influence plays a large part in performance planning. To avoid the potential for wind-induced incidents, the student must understand the impact of wind on the handling of the aircraft, as well as performance planning. One simple demonstration can be conducted while completing hover checks. Caution must be taken not to jeopardize controllability while performing this demonstration. In some cases, the instructor may need to fly so the student can focus more on the engine instruments. Position the aircraft into the wind, note the power required, then conduct pedal turns at 90 degrees increments. At each subsequent heading change, note the variation in power required and difficulty in maintaining heading control. Depending on the wind velocity, moderate to sizable increases in power will be noticed. This will facilitate understanding of the impact that directional wind has on power requirements and the importance of wind direction awareness. Additionally, this demonstrates to the student the changes in power required by the tail rotor to overcome the tendency of the aircraft to weather vane into the wind. A comparison of hover power into the wind versus with a tailwind is very effective in demonstrating this flight characteristic. In gusty wind conditions, it is also important to note the momentary spikes in torque while attempting to maintain a stationary hover. Discussing the impact of wind on translational lift best illustrates contrasting effects of a takeoff or landing into a headwind or with a tailwind. If, in a no-wind situation, translational lift occurs when airspeed reaches approximately 16 to 24 knots, then the impact of directional wind will increase or decrease that range. Noting this, the student can see the advantage of using the headwind to more quickly depart the vortices caused by in-ground effect conditions. Conversely, the student will understand that a prolonged in-ground effect condition, and the need for greater power, exists during a takeoff with a tailwind conditions, because the aircraft must accelerate more to outrun the wind and pass through translational lift. Also discuss with the student that during a landing, if there is a headwind present, it may help prevent a settling with power situation from developing. Conversely, if there is a tailwind, settling with power conditions are encountered earlier as the helicopter slows for a landing. A crosswind is much more preferable to a tailwind. The instructor should work with the student to ensure an understanding of the apparent ground speed versus airspeed factors and differences. If a pilot begins a landing approach with a 10-knot tailwind, at some time in the approach, the helicopter experiences a 0-knot airspeed, which means a total loss of translational lift and thrust. In order to maintain the approach angle, more power must be added. If the conditions of less than 10 knots of airspeed, more than 300 feet per minute rate of descent and more than 20% power is applied to the rotor system exist, the helicopter is prone to encounter settling with power. Height/velocity diagram. Ensure the student understands the information in the height/velocity diagram in the applicable post/RFM and knows how to fly to avoid those unsafe areas in the height/velocity diagram. Figure 8.2, referring to the aerodynamics of autorotation, explain that this chart shows those heights above ground and airspeeds which, in the event of engine or drivetrain failure, an experienced pilot should be able to make a safe autorotational landing. The instructor must stress that the conditions provided in the chart are ideal conditions with an experienced pilot. The instructor may wish to revisit the aerodynamic theory of autorotation. Specifically, discuss that altitude equates to potential energy, therefore, during autorotational descent the unpowered rotor system maintains kinetic energy as the descending helicopter loses potential energy in the form of altitude. Through the use of turns, flares, and collective control, the pilot can regulate the amount of available kinetic energy within the rotor system. This rotational kinetic energy in the rotor system is used during the deceleration and landing to slow and cushion the landing. If power is lost in situations of higher altitudes, Figure 8.2, Area A, and low to no airspeed, such as OGA operations, the helicopter may not be able to maintain enough kinetic energy, rotation of the rotor system, to establish the minimum rate of descent airspeed necessary for a successful landing. Also, in flight profiles with higher airspeed, Figure 8.2, Area B, and extremely low altitudes, engine failure can cause loss of altitude that will not allow time to take appropriate action to establish an autorotational profile. An effective demonstration of this phenomenon is to have the student note the amount of altitude lost during a high altitude entry into an autorotational profile and then relate this loss to what would happen in the same situation at low altitudes. It is important to stress that reaction time and an immediate response are critical for an experienced pilot to land the helicopter safely. Avoiding flight profiles in the shaded areas of the height/velocity diagram is not always possible. Some jobs require flight maneuvers or tasks with prolonged OGA operations, such as utility/power line flight, aerial photography, logging and other occupations. Have the student think through scenarios in which potential emergencies occur in these profiles. Discuss possible response options the student may have available in these scenarios. As instructors, we should be familiar with primacy. What is first learned is often the first to be retained and practiced. Take time to discuss proper takeoff and landing profiles that minimize unnecessary exposure to these shaded areas of the height/velocity diagram. These techniques may include flying higher into the wind and minimizing excessive aircraft loading. The student must consistently demonstrate these maneuvers during each flight. Performance planning. To make the discussion of performance planning relevant to the student, develop a series of exercises that are scenario-based and require use of performance graphs from the post/RFM. Each scenario-based lesson plan must have a targeted learning point. Different scenarios can demonstrate the effect of each environmental factor, atmospheric pressure, altitude, temperature and moisture, affecting density altitude. Figure 8.3 provides a scenario in which the student pilot departs a near sea level location and arrives at a substantially higher elevation. This scenario demonstrates the impact of a greater density altitude as well as the increased EGA and OGA power requirement to operate at that high altitude. Discuss with the student scenarios in which OGA power may not be available and the related consequences. Discuss aircraft system or component limitations, such as torque versus altitude-induced limitations or reductions in VNE airspeeds commonly found at higher elevations. At the arrival location, ensure the student accurately prepares departure performance planning with added fuel to return to the initial departure location, plus required reserve fuel. When possible, the scenario should use high gross weight values that best support the learning objective. If applicable, combine the effects of external loads at higher altitudes, temperatures and wind velocities. Use scenarios that provide significantly higher EGA/OGA power requirements to demonstrate helicopter capabilities or limitations and to determine go/no-go decisions based on the charted values. Instructor tips: take every opportunity to advance the student's awareness of environmental conditions. Accurate and thorough performance planning are essential to safe and successful flight operations. Require the student to complete performance planning prior to each training flight. This instills the habit and highlights the importance of performance planning. The student must use the appropriate PO/RFM for the helicopter being flown for all performance planning. This allows the student to become familiarized with the capabilities and limitations of the particular helicopter. Remember, as an instructor, you should capitalize on opportunities throughout training to correlate the academic training to practical flight applications. Tailor scenarios to the student's reason for helicopter training. Students are better able to learn when the training takes on a meaningful role and seems more relevant to the student's goals. Use techniques such as artificially limiting available aircraft power. This allows the student to experience operations in reduced performance environments, while allowing for an easier escape for the instructor while the student builds additional experience. If using this technique, the instructor must ensure the student is aware that it is only a simulation, and that actual conditions can be much more challenging. Allow the student to progress to more challenging scenarios and simulations only after mastering the basic fundamentals of the elements being taught. Chapter summary: this chapter discussed the effects ambient weather, weight, and environmental conditions have on performance planning and flight operations. Additionally, this chapter provided instructional methods to apply practical, in-flight application of academic knowledge.